Good morning to all of you. I am Aarti from BSc Chemistry Honors second year. I am preparing a video for visually impaired students regarding the chapter Chemistry of Lanthanoids. So let's we start. Introduction. The element in which the last electron enters any one of the 7 f orbital of their respective anti-penultimate shell are called f block elements. In all these elements, the s orbital of the last shell n is completely filled. The d orbital of the penultimate n-n1 shell invariably contains 0 or 1 electron, but the f orbital of the anti-penultimate shell, being lower in energy than d orbital of the penultimate shell, get progressively filled in. Hence, general outer shell electronic configuration of f block element is n-2 f0 to 14 n-1 d0 to 2 ns2, where n is equal to 6 and 7. There are two series of f block element, each containing 14 elements each. Therefore, there are 28 f block elements in all in periodic table. These elements are placed at the bottom of the periodic table. The elements of the first series, that is from lanthanum to lutetium, which forms a part of sixth period, are collectively called lanthanides or lanthanides, since all these elements follow lanthanum in the periodic table and closely resemble lanthanum in their properties. Since these elements occur scarcely in the earth crust, therefore they are also called rare earth metals. In lanthanoid, 4f orbitals are being progressively filled. The second series, 5f series, consists of elements from actinium to lawrencium and forms a part of incomplete 7th period. Since these elements follow actinium in the periodic table, therefore these elements are also called actinoid or actinides. In actinoids, 5f orbitals are being progressively filled, and these elements resemble actinium in their properties. All actinoids are radioactive elements. The first four, actinium, thorium, protactinium, and uranium, occur in nature, while the remaining 11 elements from neptunium to lawrencium are prepared artificially through nuclear reaction. These 11 elements follow uranium in the periodic table and are prepared through nuclear reactions. Therefore, these are also called transuranic or transuranium element. Lanthanoid and actinoid, which constitute the f block element, are also called inner transition element because they form transition series within the transition element of d block occurrence. Although these elements are not abundant by any means, but they are not restricted to be rare in sense in which this word was used earlier. Their substantial deposits have been found in several countries, particularly in India, Scandinavia, USA, and Russia. The most commonly occurring lanthanoid is cerium, which constitute about 3 into 10 raised to power minus 9% of earth crust. Main minerals of lanthanoid are monazite. It is most important mineral containing lanthanoid. It is essentially a lanthanoid orthophosphate. Some monazite dependents contain appreciable amount of thorium also. In some cases, thorium may be present to an extent of 30%. It is interesting to note that elements with even 11 atomic number are relatively more abundant and also have a larger number of isotopes. The elements with odd atomic number are less abundant and do not have more than 2 isotopes. Promethium does not occur in nature and have been prepared artificially by radioactive disintegration. Basinite. It is mixed fluorocarbonated where M is La or lanthanoid. Monazite and basinite have almost similar distribution of metals, except that monazite contains approximately 8 to 10% TiO2 and 3% deuterium earth, which are almost not there in basinite. Large amount of basinite minerals are found in California, Sweden, and New Mexico. Cerite. It contains silicate of cerium in Sweden and Norway. Some other minerals which are found in small amounts are cryolite, genoite, axonite, and galenite. Electronic configuration and position of lanthanoid in the periodic table. Lanthanoid involve the gradual filling of 4f orbital. The ground state electronic configuration of each lanthanoid element has 2 electrons in 6s orbital. Since the energies of 6s, 5d and 4f are nearly equal, therefore the order of filling of the 4f orbital in atom show some irregularities. At lanthanum, both 5d and 4f orbital being stable due to increased effective nuclear charge because of poor shielding effect of 6s orbitals. It is therefore observed that at lanthanum the incoming electron enters the 5f-d orbital and electronic configuration of lanthanum is lanthanum Genome 54 4f0 5d1 6x2. However, on moving further after lanthanum, the energy of 4f subshell becomes distinctly lower than the 5d subshell, and therefore the next electron in cerium enter 4f subshell. The electron configuration of cerium therefore is represented as 6x2 5d0 6x2. This stand of filling 4f orbital continues further until we reach ytterbium, in which 4f subshell get completely filled. Yes, thus ytterbium has electronic configuration 5d0 6x2 4f14. These are elements of lanthanoid: lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, europium, thorium, ytterbium, lutetium. General characteristics of lanthanum element. Some important characteristics of lanthanum element are discussed below. Ionization energy. Lanthanoid have very low value of first and second ionization energy, and these values are comparable to calcium whose first and second ionization energies are 590 and 1150 kJ per mole respectively. The first and second ionization energy of lanthanoid increase in general but show little variation with atomic number across the lanthanoid series. The trend is more clear for some of three ionization energies than the first ionization energy. Oxidation state. The most common oxidation state of all lanthanoid is +3. Lanthanium show +3 oxidation state through the loss of both the 6s orbital and hence also the solitary d electron. The configuration of La3 positive ion evidently is that of xenon, which is highly stable. Since it is not possible to remove another electron from this structure, therefore higher oxidation state of lanthanum is ordinarily not possible. Color and spectral properties. Some trivalent ions of lanthanoid series are colored in solid state as well as in their aqueous solution. These colors are shown in table 1.5. Since the color remains same even on change of an ion, therefore color seems to be characteristics of particular lanthanoid ion. The color of lanthanoid ion arises due to absorption of light from visible region of the spectra, resulting in the electronic transition with 4f level called FF transition. A remarkable feature of spectra of tri-positive lanthanoid ion in the sharpness of the individual bands. They even become more sharp and line-like with a lowering of temperature. This behavior is in contrast to the absorption band of DD transition, which have broad absorption band. The main reason for the sharpness of the band is that 4f orbital lie deep in the atom and are shielded effectively from the surrounding by the overlying electron in the 5s and 5p orbitals of the rare earth ions, and hence absorption band arises merely from electronic transition with the 4f level. Thus the absorption band show little dependence on the nature of ligand. Magnetic properties. The La3 positive, C4 positive and Yb2 positive ion which have 4f0 and 4f14 electronic configuration ion, that is do not have any unpaired electron, are diamagnetic. The rest of trivalent lanthanoid ions which contain unpaired electron in the 5f orbital are paramagnetic. The magnetic property of lanthanoid are different from those of transition element. In a matter of common knowledge that magnetic movement arise from two types of motion of electron, one due to spin motion of the electron around in its own spin axis called spin magnetic momentum, and other due to orbital motion of the electron around the nucleus called orbital magnetic moment. Both these both these magnetic moments combined together determine the magnetic properties of lanthanoid. The formula of magnetic spin is mu is equal to under the root n into n plus 2, and the formula for spin magnetic moment is mu is equal to under the root 4s into s plus 1 plus l into l plus 1. Oxidation potential. The standard oxidation potential of lanthanoid for the half reaction Ms M3 positive plus 3 electron are quite high and are in accordance with their electronegative character. This is, however, a slight decrease in the oxidation potential as we move from La to Lu, lanthanoid to titanium. This is consist with the slight decrease in ionic radius due to lanthanoid contraction. The standard oxidation potential for the above half reaction are given in table. Ionic radii. The lanthanoid contraction. As we move across a period from left to right, there occurs a decrease in size. This can be attributed to the increasing effective nuclear charge, because of which the outermost shell of electron is attracted more and more, thereby decreasing the size. If we compare the general decrease in size in moving across a period with increase in most stable ionic radii, in case of lanthanoid, we find that decrease is very small as compared to decrease found in another period. For example, it has been observed that in moving from cerium 3 positive to lutetium 3 positive, the ionic radii decrease from 103 pm to 86 pm only. So in this video we discuss about general properties of the lanthanoid. Thank you.